Hey guys, welcome to my channel. This is Miss Wow to give you something to say wow about. Some sneak peek. Today's live streaming is awesome. I invited top Chinese experts to tell you everything you need to know about the recent Chang'e-5 lunar exploring mission. There will be also some unknown stories behind this mission, and we will launch an online Q&A. So don't miss out the opportunity, the very precious opportunity to ask straight to the Chinese top space expert, Mr. Yang Yuguang. Mr. Yang, I'm so lucky to join you here to talk to us about the lunar space.
Hello, everybody. My name is Yang Yuguang. I come from China Aerospace Science and Industry Corporation Limited. I am a system designer, mainly engaged on space system design and spacecraft design. I also work for the International Astronautical Federation as the vice chair of the Space Transportation Committee. I also is the founding member and also regional coordinator for Moon Village Association. Good evening.
Okay, welcome. Thank you for being here. So after weeks of space travel, China's Chang'e-5 has come back to Earth with fresh lunar rock and soil samples on Thursday morning. The precious cargo is the first lunar samples that humanity has obtained in more than 40 years. So please subscribe to my channel, Miss Wow, on Facebook, Twitter, and YouTube, and also Instagram to know more about the most mind-blowing China innovation stories. So, long story short, China sent a probe to the moon, collect the lunar sample, and then come back. So it sounds a mission impossible, right? So keep watching. We will figure it out. You won't regret it. But remember, this is not a class, but for somewhere for you to play and to discuss. So leave your comments below if you have any questions, and we will answer it for you. So it is a very rare opportunity for you to invite such an expert to give you answer about the space. So feel free to bring them on. So first, let's review the marvelous moments of the Chang'e-5 rocket launch and the new Chang'e-5 returns to China, to Earth.
I believe this is the Hainan Wenchang spacecraft launch site. So this is the ignition of the Long March 5 launch vehicle, and it's already lifted out from the launch pad, and the tower is cleared. And you can see, okay, so this is the image of the separation of the probe and the rocket. You can still, this is from the camera of the launch vehicle, and also this is the unfolding of its solar panels of the probe. And from this moment, it can get energy from the sun continuously. And also, the lander will also unfold its solar panels. So you can see that this is a way from the Earth to the Moon, which can be called the Earth-Moon transfer orbit, which is a high elliptical orbit with the perigee or the lowest altitude about 200 kilometers, and the highest point or the apogee about 380,000 kilometers, or even 400 kilometers away.
Yeah.
So they rendezvous with the Moon. And when it approaches the Moon, there is a very critical step called the lunar orbit insertion. It must reduce its speed with its 3,000 Newton rocket engine, and then entering the circumlunar orbit. But this will be done with two operations, and then will be the separation of its 4 modules, and then landed on the Moon. So you can see this 3D animation. and the orbiter will still orbiting the moon. So the lander and also the ascender will be a combination and land on the moon for the sample collection. And after collection, the ascender will lift off or launch from the lunar surface with the lander as a launch pad. And then they will go back into the lunar orbit and rendezvous docking with the orbiter-returner combination. So this is from the view of one of the combination. And they will dock. On the left side is the orbiter and the returner combination, and on the right side is the ascender. The claws grabs, and then will be the sample transmission. The sample transfer from the ascender to the returner. The mechanism will move 4 times to make the container from one side to the other side. And then will be the separation of the ascender and the orbital module. Then the orbiter will wait in the lunar orbit, and then with the orbit insertion from the circumlunar orbit to the transfer orbit to the Earth. At the altitude about 5,000 kilometers, there will be another critical point, the separation of the of the returner and the orbiter. Then the returner will on its own, with a skip re-entry, finally landed in Inner Mongolia in Sivang Banner. But not like this animation that will be at night.
Wow, reviewing such marvelous moments, I feel like goosebumps. What about you, Mr. Yang?
Well, you know, that's from 24th of November, I'm very nervous for every step.
Yeah.
You see that this is the last step for our 3-step strategy, orbiting, landing, and returning. But in each step, there are very critical steps and very risky. For instance, during the transfer to the moon, the orbit insertion from the translunar orbit to the circumlunar orbit is a very critical point and very dangerous. If we miss it, the whole probe will miss the moon and go to other places, never back. So we only have one chance.
Yeah.
And the landing is also full of risky. You see that just several months before, the India and Israel suffered failure on soft landing. So their probes crashed on the lunar surface. Not because they are doing not well, just because it's too difficult. So these are also, although we've already done this before, but still these steps are very dangerous. And after soft landing, all the following steps are new for Earth. And even some of them are the first in the world. So you see, we will discuss this later, but so many new steps. And finally, landing in Inner Mongolia, my homeland. So I'm so proud of my colleagues and my friends in this field, and it can be really called a great achievement and a very important milestone for China Aerospace.
Yeah, so it is so challenging, but now I feel so proud of our Chinese technology. So back to the original theme, we know that Chang'e-5's mission is to get a lunar soil sample and then come back, right? But at the first place, why we have to take it? What's so important about the lunar soil samples?
Well, you see that from the human civilization, the moon plays a very important role for Earth.
Yeah.
You see that the whole solar system was formed about 4.6 billion years before.
Yeah.
And the Earth and the moon was formed at that era. And there are many hypotheses about how the moon was formed. There are different theories. But each theory are not very perfect. But the most recognized series is giant collision series. So billion years before, there is a primitive planet with a size like the Mars called Terra. It collided with the Earth, and some of the material from the Earth were collision and raised to the space. And then the combined together again and form the moon. So this theory is the most recognized, but still not very perfect. We still need evidence to prove that it's correct. So that is the answer of your question. We need to study the origin and the history of the moon. And this is also very important for us to understand the so-called the Earth-Moon system. Because you see that we have 4 seasons: spring, summer, autumn, and winter. This is because we have the moon. Because of the moon, we have this stable season change. And the similar things is quite different in the Mars. Because the Mars, although they have 2 moons, Phobos and Deimos, but they are too small. So the moon is very important for us. Moreover, you see that we study the history of the solar system is to predict the future or the evolution in the future of the solar system. So this is not only for scientific research, but very important for us to know the destiny of human being. So you can see how important it is. So these are the scientific research goals, but also there are engineering goals. You see, since 1990s, some of the probes from other countries has already found water on the lunar surface. And also, after the Apollo program, the scientists found helium-3 in the samples getting back from the moon. So the moon has very useful resources for us. Maybe in the future, if the controlled fusion power can be solved, the helium-3 will be the ideal fuel for the fusion power. Some experts say that it can meet the requirement of energy of human being for more than 10,000 years. So,
wow.
And some person say that the moon will be the Persian Gulf of the 21st century. And for the near term, you see, because water is found on the lunar surface, it can not only be drank by the astronauts in the permanent base on the lunar surface, but can also produce hydrogen and oxygen, which are ideal propellant for the spacecraft. You see that the human being has missions to the Mars, but still the cost is the most serious problem. But if we can produce the propellants on the lunar surface, because the moon is much smaller than the Earth, so it is possible to reduce the cost to go to Mars. Then we can recognize the moon as an outpost of human being for Earth to go deeper into space, such as the moon, such as missions to Mars, and even go beyond. So you can see from the aspects of scientific research and from the aspect of engineering, the moon is all very useful. So that is the reason why the moon, after the Apollo program, you see that for almost half a century, there's no one revisit the moon. But today, many countries have a plan to revisit the moon and even man mission to the moon.
Okay, so this time we created lots of firsts. So could you please tell us which first we have been created?
Yes, we have so many firsts. So as I mentioned before, after landing is a very critical step for our Chang'e-5 mission, but we've already done that before in Chang'e-3 and Chang'e-4 missions. But this time, the first thing we should do, we have never done before, is collecting samples on the lunar surface. So you see, because this is, although Russia or the former Soviet Union and the US has done that, but we haven't done that before. There are many difficulties and challenges. For instance, the lunar surface, the environment is very, very crucial. You see, the temperature, the lowest temperature can be below about 200 Celsius degree, below zero. And the highest temperature under the sunshine can up to about 100 Celsius degree. So you see, it is an extreme hot and extreme cold environment.
Yeah. And
also, there are lunar dust. You see that the dust on the lunar surface, they are very, very tiny, very, very small powders. And these powders, if they come into the moving parts of our robotic arm, it may cause failure of these arms. So we must consider the influence of this lunar dust. And also, you see that the radiation on the lunar surface is really, really serious, much more serious in the low Earth orbit. You see that we have astronauts in our Shenzhou spaceships, in Tiangong laboratories, and in other countries, they have astronauts on board the International Space Station. But all these are orbiting the Earth within an altitude of about 400 kilometers. At this range, these astronauts or spacecraft can be protected by the magnetic field of the Earth. So there is no much radiation like the moon. So we must consider that the environment, including the radiation, is more crucial than the low Earth orbit, so the collection of samples is really difficult. we must consider that. And it is very interesting because this is the first time we do it, so we have very good simulations on the ground. So in the China Academy of Space Technology, we have a building which can have very good simulation environment, and also based on the image taken by the Chang'e-5 lander, which we have a landing camera and a panoramic camera. So you see that this photo on the top left is a photo we taken by the panoramic camera of the lander. So with these photos, we can reconstruct the simulated surface of the moon, and then we can have a remote control of the robotic arms and our sample collecting mechanism. So with these kind of measures, we can be more reliable for the success of the sample collection. So this is the first.
Yeah.
And the second first is that we must lift off from the lunar surface. So the ascender is taking this role, and the lander act as the launch pad. But it's quite different from launching a spacecraft from the ground. You see that if we launch a rocket, like this time the Long March 5 from the ground, we have all kinds of support. The coordinate of the launch pad can be measured very precisely. And the attitude of the vehicle itself can be measured by all kinds of instruments. And also, we have connections, the cables, either cables connections or the wireless connections. We can monitoring the status of the launch vehicle and the spacecraft. So we have all kinds of support. But on the lunar surface, we only have limited support. You see that the lander, the site, is to the north of the so-called Mount Ramaker region. And this place is, please remember, is more than 880,000 kilometers from the Earth. So even the communication is based on radio wave, and even the one-way communication, we need more than 1 second. So there is a very serious delay.
So Chang'e have to count on itself.
Exactly. So to a great extent, although we can have control from the ground, but it greatly depends on the vehicle itself. So we have the ground stations to measure the trajectory of the ascender, but it's mainly on itself. So liftoff from the lunar surface is very, very dangerous part. And also, there are another influence. For instance, because this time, before the mission, we don't know the coordinate where we lift off. And we don't know the attitude of when we lift off. So after we collecting samples, we must measure the coordinate of the lander. And then we measure the attitude of the lander. So we can have this kind of basic data necessary for liftoff. And then the ascender liftoff from the lunar surface. And also, we must consider the flame, because the flame have influence to the rocket engines and to equipments on board the ascender. So this is the second first. We never done this before. And the third one is not only the first in China, but also the first one in the world. It's called the unmanned rendezvous and docking in lunar orbit. You see that the ascender first lift off from the moon and entering orbit with the lowest point about 15 kilometers and with the highest altitude more than 100 kilometers from the lunar surface. And because you see that there is a very interesting phenomena. When this ascender lift off from the moon, you can see from the flight control center that the orbiter is orbiting the moon on the southern hemisphere, while the ascender lift off from northern hemisphere. So there is no conflict, because you see the basic requirement for the rendezvous and docking is to require the both vehicles to launch into the same orbital plane. So this is very important. But the position doesn't matter, because you see that, as I mentioned, the ascender entering a orbit lower than the orbiter, so it moves faster than the orbiter. So it is the chasing vehicle chasing the orbiter, one orbit, another orbit, and then finally it goes beyond the orbiter, and finally it goes into orbit, a circular orbit with the altitude about 210 kilometers. And then at this moment, they exchange their role. So the orbiter becomes the chasing vehicle and chasing the ascender. And then when they approach to a distance within 50 kilometers, so the long distance guidance ended. And then the rendezvous approach is each other mainly based on the instruments on board themselves. We have a rendezvous and docking microwave radar, and also we have a LiDAR based on laser, and also we have optical sensors to help them to know the relative position, relative velocity, and relative attitude to each other. And also they have communication links based on the rendezvous and docking radar to communicate and exchange data with each other. And of course, this is also monitored by the ground, but mainly on themselves. So they dock with each other. I emphasize again, this is the first time we human beings do it on the lunar orbit. The Apollo have done this several times, but they are manned rendezvous and docking. Although you see that the manned or automatic docking is more precise, more accurate than the manned docking, but the manned docking are more flexible. And you see in some certain cases, the astronauts can dealing with these kind of dangerous things. So you see, this is the first time in the world. Very, very dangerous. So another first is the first time we coming back from the moon with samples. We experience a skip re-entry at a speed about 11 kilometers per second, very close to the second cosmic speed. Nominally speaking, the second cosmic speed is about 11.2 kilometers per second. So you see that this is also very dangerous. Because the aerodynamic heating is much more serious than the Shenzhou spaceship. And to reduce the cost of the heating shield of the returner, we do have a very special design, choose the skip re-entry. We will talk this later. So this is also another first. And finally, we will first establish a special laboratory to dealing with and study the lunar samples. This is also the first for China. So you can see we have so many firsts. And for every step, it is very critical, very risky, very dangerous. I'm really nervous at that moment.
Yeah, so we say this mission is very special, and also because, you know, the Chang'e 1, 2, 3, 4, they all launched by the Long March Series A. But this time we built this brand new Long March 5. So what's so special about this rocket?
So you see, this is a very long story. You see, Long March 5 belongs to our new generation launch vehicles. Our old generation launch vehicles currently in use are Long March 2, 3, and 4 series. All these can be recognized as the derivative of the Long March 2, which was developed in about 1970s. All the old generations are used the propellants with the UDMH, or unsymmetrical dimethyl hydrazine, as a fuel, and use the nitrogen tetroxide as the oxider. These propellants do not have a very high performance, but they have advantages because they can be stored in room temperature. And then when they meet with each other, they can burn automatically. So the design of the rocket engine is much simple. So Long March 2 is the, actually speaking, Long March 1 is the first one of our Long March series, which was first launched in 1970. So it was the first to launch the Dongfang Hong 1 satellite into space. But the Long March 2 we developed, the first launch attempt was failed in 1974. And the first successful one was in 1975, which launched successfully of our first retrievable satellites. And after that, we have multiple derivatives. Long March 2 series, now currently we have Long March C, Long March D, and Long March F. Which are all derivative of the Long March 2. And also we have Long March 3 series. Long March series, as you mentioned, now we use the Long March 3A series, all with a diameter of 3.35 meters. And the distinct feature of Long March 3A series is that it has a third stage. The third stage uses the high performance liquid hydrogen and liquid oxygen as the propellants. So Long March 3 series usually used to be launching the payload into a very high altitude, such as the geosynchronous satellites and also the lunar probes. And the Long March 4 series also have 3 stages, but quite different from Long March 3 series. Their third stage use room temperature propellants like the first and the second stage. So you see all these derivatives of the old generation all based on the 3.35 diameter modules. So they have similar technologies. And you see for the new generation, we have Long March 5, Long March 6, and Long March 7 launch vehicles. Their features is they all use kerosene and liquid oxygen as a propellants. And also some, like the Long March 5, also use liquid hydrogen and liquid oxygen as a propellants. So you see that the old generation, the propellants, have some shortcoming. For instance, the UDMH, the fuel, is highly toxic. Yeah. And the NTO, or the nitrogen tetroxide, the oxider, is highly corrosive. When it meets water, it can be changed into nitrogen acid. So you can see how dangerous and how difficult it to deal with. But for the new generation, we use liquid oxygen, kerosene, and also liquid hydrogen, which are environmental friendly and also have high performance. So our new generation, the first one launched was Long March 6, which is a very small launch vehicle. In all these, our new generation launch vehicles, we use the so-called YF-100 rocket engine, which is a very high-performance rocket engine with thrust on the ground about 120 tons. The Long March 6 use only one this kind of engine on its first stage, so it's a very small launch vehicle. After successful launch of this launch vehicle, we test the launch of Long March 7. Long March 7 has a core stage, as I mentioned, with a diameter of 3.35 meters, and with two these kind of YF-100 engine on its first stage, and also it has 4 boosters, each have one this kind of engine. And Long March 7 has a capability to launch about 14 tons of payload into low Earth orbit. So it is used to be launched the Tianzhou cargo ship for our future space station. And after this launch, we have the test launch of Long March 5. So Long March 5 is the most powerful launch vehicle in China's launch vehicle family. And the most distinct feature is that the core stage is 5 meters. So I will tell you the reason. You see that during the years before, we China have 3 launch sites or launch centers: the Jiuquan Satellite Launch Center, the Taiyuan Satellite Launch Center, and Xichang Satellite Launch Center. We all need to transport our launch vehicles, the rockets, to these launch centers by train. And you see that, you know that the train has to passing through the railway tunnels. You see, because of the limitation of the size of or diameter of the railway tunnels, so the diameter can only be 3.35 meters. That's the limitation of our choice. But you see, we want to have a bigger rocket, it cannot be too long and still too thin. So in the new generation launch vehicle, we choose Tianjin to build the factory to produce these launch vehicles. And we choose the Hainan, the Wenchang, to build our new launch site. So with this choice, we can ship the launch vehicle transport the launch vehicle from Tianjin to Hainan by ship. So there will be no limitation of the diameter. Theoretically speaking, we can have even bigger diameter. So with this configuration, the Long March 5 launch vehicle, the core stage can be 5 meters. Much bigger than our old generations. So with this, it can have a very powerful liftoff, and it has also have 4 boosters. Notice that the 4 boosters, although it's smaller than the core stage, but the diameter is 3.35 meters. So the boosters has the same size of our old core stage of launch vehicles. So you can see how big it is. And the capability of Long March 5 is much more bigger, even twice more than the Long March 3A series, as you mentioned. So this time we use our most powerful launch vehicle, Long March 5. You see that, as you mentioned, from Chang'e-1 to Chang'e 4, and including the Chang'e-5 T1, which is a test mission for the Chang'e-5 this time, we use the Long March 3A series. We use the Long March 3A, which only have a core stage, to launch the Chang'e-1. And with Chang'e 2, we use Long March 3C. Long March 3C is based on the Long March 3A and added 2 boosters. So it's more powerful. And it can launch the Chang'e 2 directly from the Earth to the transfer orbit to the Moon. Well, the Chang'e 3 and the Chang'e 4, because they are landing missions to the Moon, so they are much more heavier. The mass of these 2 probes are about 3.78 tons, much more heavier. So we use the most powerful launch vehicle of our old generation, Long March 3B. Long March 3B is based on Long March 3A, but with 4 boosters, so it's much more powerful. The capability to the moon is about 3.8 times, so it's big enough for the Chang'e 3 and the Chang'e 4 missions. But you see, for the Chang'e 5, because it's much more bigger, much more heavier, so the mass is 8.2 tons. So the Long March 3A series do not have the capability to launch so heavy payload into to the moon. So we only have this choice, Long March 5, to launch this payload.
Yeah, so I think that's why our user gave him a nickname called Fatty, like Fatty Long March 5. Right?
Exactly. You see that from our professional field, we have a word called aspect ratio. Aspect ratio is the ratio between the length of a launch vehicle and its diameter. So it cannot be so big. If it is too big, that means the launch vehicle will be too thin and too weak. During the flight, it may be damaged by the aerodynamic forces and other disturbance. So but you see that during years before, if we want to have a bigger rocket, because we only have the limit, as I mentioned, the railway tunnels, so the diameter is fixed one.
It has to be a reasonable range.
Yeah, or another choice is to have added boosters, but also have limited. We can't have so many boosters. Yeah. So finally, if we want to have a bigger rocket, the only choice for us is to have a bigger diameter.
Yeah. So this mission is supposed to happen 3 years ago, but due to the failure of the Long March 5 launch, so it's kind of delayed. So what went wrong 3 years ago? And the scientists took some 1,000 days to find out, to explore the reason behind that. So do you have some behind-the-scene stories to tell?
Yes, this is a very long story. You see, originally, we want to launch the Chang'e 5 first, and then Chang'e 4.
Yeah.
Because the schedule is on at the end of the 2017. You see that we hope that the Chang'e 5 probe can be launched by the Long March 5 after 2 continuous success of the Long March 5. Well, you see, the first launch attempt of Long March 5 is a success in 2016. Yeah. But unfortunately, it failed in the second launch attempt in 2017. The failure comes from the rocket engine called YF-77. So we can see, we don't have a figure here, but we can see, I can describe. So the Long March 5 vehicle have a core stage and 4 boosters. The 4 boosters are based on 3.35 meter modules. With each of the booster has 2 rocket engines, 2 YF-100 rocket engines based on kerosene and liquid oxygen as the propellants. So these are very powerful. You see that each engine has a thrust of 120 tons. So the 8 engines has a thrust of more than 960 tons. So they provide most 90% of the thrust when it lifts off. But the core stage, remember, the core stage have 2 stages. The first stage uses the so-called YF-77 rocket engine. And it uses 2 of these engines. As I mentioned, the thrust on the ground, on the sea level, is about 50 tons, while in vacuum condition is 70 tons. The most distinctive feature is that it is the most high performance, has the highest performance in our rocket engine families, because it uses liquid hydrogen and also liquid oxygen as a propellant. And also the core stage has a second stage, which also use liquid oxygen and liquid hydrogen, but with a different, smaller engine called YF-75D. So what you mentioned as failure comes from the malfunction of the first stage. So you see, during the launch of our second attempt of Long March 5, after the 4 boosters were separated from the core stage, so you see at this moment the Long March 5 is mainly based on the core stage itself, and one of the 2 YF-77 engines has a drop of thrust. So the drop of thrust caused very serious consequences. You see that during the launch, if the thrust is smaller, because there are certain amount of propellant, it must work longer. But it does not have the chance or have the time. So finally, because the thrust drops, because this malfunction of the rocket engine, it cannot go into the orbit and then deorbited into the atmosphere. So that's a very serious failure.
Yeah.
So after this failure, we canceled the launch by the end of 2017 of Chang'e-5. So our engineers paid their attention to solve the problem of this YF-77 engine and found that there are some malfunction on its turbo pumps, which provides the pressure to the rocket engine, to the combustion chamber from the fuel tank. So by many technical measures and by many ground tests, we finally solved this problem. And after this, we launched the Long March 5 again, but not the Chang'e-5. We launched that with a very heavy satellite. So it can be called the first satellite of the Dongfanghong 5 satellite series. So with this launch, it proves that the Long March 5 is reliable. We can use that to launch operational payloads. After that, you see there is a very interesting choice. You see that the launch window for Mars probes happens every 26 months. So you see, because you know that if we miss this launch window this year, we have to wait for another 2 years. So we don't have a choice. We must launch the Tianwen-1 first, before the Chang'e-5. So you see, that's this year in July, we launched the Tianwen-1 Mars probe of China with the with Long March 5. And then, because this is to catch up with this launch window, so the Tianwen-1 is already on its way to Mars. And after this, the most ideal launch window comes for the Chang'e-5. So after this launch, we launched the Chang'e-5 in November. So this is a very good launch window. So you can see before the Chang'e-5's launch, we already have 2 continuous successful launch of Long March 5, which proves that it is reliable. And then only at this moment we can launch the Chang'e-5. Moreover, you see, we meet another serious problem. You see that for any spacecraft, including its subsystems, its components, its parts, there is a limited lifespan of storage. So originally, the Long March 5 is planned to be launched in 2017, but this year is 2020.
Yeah.
So it's stored on the ground for 3 years. Many of the lifespan of the components are expired. So this is a really serious problem. So our designers and our engineers must handle and study how important and how serious this problem is. So we have many measures. For instance, we stored the Long March 5 in an environment full of nitrogen. Because you see, nitrogen is not very active. It's not chemically speaking, not like the oxygen. And also, the storage environment has almost no water vapor. You know, water vapor is also very harmful for storage, store anything. Yeah. So with these kind of measures, we can ensure that the Chang'e-5 is properly stored and can be launched this year. So there are many these kind of stories. So finally, we can launch that on the 24th of November.
Yeah. To showcase it more clearly, we can come to the whiteboard.
Yes.
Yeah. Okay, let's make some space. Mm-hmm. The mission, the mission sounds really simple because that's the Earth, right? And that is the moon.
Oh, sorry.
Many people think that we send a probe, come to the moon, then do some drilling and digging the moon soil sample, and then come back. But it's not that simple, right? It's far more complicated than that.
Far more complicated.
Yeah. So show us what is the process of the working.
So we have these pictures help us to understand the whole procedure. Yeah. You see, the Long March 5 is launched from the ground into orbit, but still have many steps. Yeah. So there are. Actually speaking, I will show you. So this is the Earth. Yeah. And this is the Wenchang spacecraft launch site.
Yeah, the launch site.
And after liftoff, there are many critical. Oh, sorry, we use this pen. Yeah. We will have many critical steps. So the first one is pitch over. Yeah. Because you see that the Long March 5 liftoff vertically. Yeah. And it has to go to another direction. So the first operation is to, after the tower is cleared, is to pitch over and change its direction to the eastern woods. And then the second critical step is the separation of the 4 boosters, as I mentioned. So the failure of the second launch attempt happened after the separation of the 4 boosters.
Yeah.
And then will be the separation or jettisoning of the payload fairing. After the separation of the boosters, the third critical step will be the separation of the payload fairing. After that, we will have after the first stage using up all its propellants, it will be the separation of the first core stage. Then the payload is mainly on the second stage. So the second stage have a very complex procedure.
Yeah.
So it will work for several seconds, and then it will shut down for the first time. At this moment, the Long March 5 already, theoretically speaking, is already entering the orbit, but a very low orbit with the altitude about 200 kilometers. After that, the vehicle will have a free flying, which is called a coasting phase. So the reason for this choice is that because you know that China is not located on the equator. Although the Hainan province is the most southern province of China, but still the Wenchang satellite has a latitude about 20 degrees, so still not lower enough for Earth. So we have a coasting phase to let the vehicle to fly to the southern hemisphere of the Earth and very close to the equator.
Yeah.
At that moment, the second stage of Long March 5 ignite again. This operation is called perigee kick. As I mentioned, from the first shutdown, it's already entering orbit with the altitude about 200 kilograms, a circumorbit. But they do not experience the whole orbit. So after the first shutdown, it have a coasting phase, go to a place near the equator, and then ignite again. And at this point, it's accelerated from the speed about 7.8 kilometer per second to about 11 kilometer per second.
Oh,
and
quite
then,
a booster.
Yeah. So this is called a perigee kick. Perigee kick and makes the vehicle to entering a high elliptical orbit with the apogee about 200 kilometers and with the perigee about 200 kilometers and with the apogee about 400,000 kilometers.
Wow.
So it's a very thin high elliptic orbit. So this is called the Earth-Moon transfer orbit. And then it will stay in this orbit for about 112 hours. During this long procedure, it will perform 3 mid-course correction or trajectory correction maneuver. So these are very important. So you see, this is because the reason it is a very long journey for about 4 to 5 days. So even a very slight error at the initial stage will cause a very big error at the end. So we need the mid-course correction. At this place, we will measure the orbit, measure the position if it is correct. If it has a very big error, we will correct it. And also, we have the purpose of testing our rocket engines on board Chang'e-5.
We have to perform precisely on every single step.
Exactly, because you see, the next after the 3 mid-course correction, the next step will be the lunar orbit insertion. So it's near the moon. With the altitude about 400 to 200 kilometers above the moon. At this point, you see, if we don't have an orbit maneuver because of the features of orbital dynamics, the Chang'e-5 probe will fly by the moon and going away, never go back again. So this is a very important point. As I mentioned, I'm very nervous at this moment. So at this moment, the rocket engines on board the Chang'e-5 will work for a very long time. Actually speaking, the 3,000 Newton rocket engine on the orbiter will work for about 22 minutes. So it's slowing down the speed of the vehicle to an elliptical orbit, orbiting the moon. And then so at this moment it's already orbiting the moon, so it will not going away. And after this, it will work again to reduce the speed, and then it finally entering a circumorbit with the altitude about 200 kilometers. So you see that we've already done this before by all the Long March 5 to Long March 4 probes, but still because it is very dangerous and we only have one chance, so it's very risky and dangerous. And after this, there will be a separation. Let's look at this picture. Oh, sorry. You see that the Chang'e-5 probe is have 4 major modules. The first one is the orbiter. And the second one is the returner. From low to high. And then the lander and the ascender. So these 2 are also very important. This is a supporting structure. And this is the docking and the sample transfer adapter. We will talk this later. So after they have already go into the circumlunar orbit, there will be a first separation. So at this moment, the orbiter and the returner will form a combination. And also the ascender and the lander will form a combination. So the first separation will be the separation of these 2 combinations. And then this combination will still orbiting the moon at the altitude about 200 kilometers. And then the combination of lander and ascender will land on the moon. As shown on this, but this is also a very complex procedure. You see that because still for landing on the moon, a soft landing on the moon, 200-kilometer orbit is still too high. So there is a first orbit maneuver of this combination is to lower its orbit, the lowest point from 200 kilometers to about 15 kilometers. So this is the first maneuver to reduce its speed here, and the altitude here will be changed to 15 kilometers. And then from this point, we can have descending. All because you see that the moon is a vacuum condition. We all based on the rocket engines. So this will be so-called a powered descending. So the first, because you see that at this point the speed is about 1.7 kilometers per second. So at this point, we need to reduce the speed to 0 and also reduce the altitude from 15 kilometers to 0. We use a lot of propellants. So the lander will use almost all its propellants after landing.
So all these moves, it perform automatically or it follow the constructions from the Earth? It
is performed automatically. But also we have monitoring from the Earth, although there are 1 second delay. It is a very special procedure. You see that we have multiple ground stations. China also have a very good deep space communications network, which can support our Chang'e-5 missions and also can support our Tianwen-1 Mars missions. So we have very large antennas in Jiamusi station. Jiamusi is in northwest China. So you see, let's put this photos here. Okay.
Check the Chang'e-5.
Okay.
So
we don't use this photo. We can please. Yes. Look. So you see, this is our China. And in the eastern part, we have a station in Jiamusi. And Jiamusi is almost the most eastern part of China. We have antenna with very huge antenna with the diameter about 66 meters. Very huge. So this is a main deep space station. And also we have a station in Kashi. Kashi is in Xinjiang and also almost the most western part of China, which have 4 antennas with a diameter of 35 meters, also very huge. So these are 2 deep space stations. And also we have another station outside China in Argentina. We also have an antenna about 35 meters dish. So with these 3 dish stations, we have a continuous communication link with the Chang'e-5 probe. And also, as you asked, during the orbiting, and also during the transfer, and also during the descending, all these procedures, we have communication links based on these 3 stations. And also, they have other important roles to measure the orbit of the vehicle, because this is also very critical and very necessary for our steps. And also, besides this, we also have other special measures. For instance, we have astronomy observatories in Beijing, in Shanghai, in Kunming, and in Xinjiang. So all these 4 stations form a so-called, we call this very long baseline. Very long baseline interferometry. With this, we can measure the accurate angle of the position of our vehicles.
Okay.
So this has already been used in Chang'e-5 mission since then. So this is also the VLBI is very important for measuring the orbit of our vehicles, especially this combination. Because you see that during the landing phase and the ascending phase, it is very important to have the very precise trajectory. And with this measure, we can have almost a real-time measurement of this trajectory. Very, very necessary. Because you see that the difference from rendezvous docking near the cislunar space is quite different from that of the Earth. Near the Earth, because you see that we have multiple support. Near the Earth, you see we have Beidou navigation satellites. Yeah. The Beidou navigation satellites can give guidance to these kind of launch vehicles. But there is a problem. You see that the Beidou navigation satellites, the altitude of the Beidou navigation satellites have two configurations. One is at the altitude about 36,000 kilometers high, and the other is about 20,000 kilometers high. So they are much lower than the moon. You see that the radio beams of the navigation satellite is like this. So they can cover the low Earth orbit, and our Shenzhou spaceship and our Tiangong laboratory can use the navigation signals of these navigation satellites. But you see that is much higher on the moon. There is no signal. So this is a problem. And also on the ground, we have multiple stations which is very close to the low Earth orbit, so they can get support from the ground stations and also from the data relay satellite. But on the moon, nothing. So it's to a great extent on itself. So during the landing, we use these kind of deep space networks, and also we use the VLBI, but still these are very limited comparing with the requirement of the rendezvous and docking. Yeah. So so during this procedure, the landing we also use the all kinds of instruments, such as the laser array. With the laser array, we can find big obstacles on the lunar surface, and to avoid to land on this place. And also we have other sensors, and we have a gamma ray altimeter. When the lander is about 4 meters above the moon, it will shut down its engine. This is to avoid the influence of the lunar dust to the vehicle itself. So this is also a technology which be tested by the Chang'e-3 and the Chang'e-4. Okay. So after landing, you see, after landing, we will, as we already discussed, we will have the sample collection, which is very, very complex. You see, you can see from this picture. So this picture is taken by the panoramic camera on board the lander. Our lander, besides the sample collection payloads, we also have other scientific research payloads. We have a landing camera, which can get images or videos during the landing procedure. We also have a panoramic camera to monitoring the whole situation near the landing site, like this, the photo taken by this one. And also, we have a lunar penetrating radar, which can get image or get information from several meters beneath the surface. And also, we have infrared spectrometer to measure the components of the lunar surface. Okay. So these instruments can help the covers to get the right samples. So on the lander, the major payload is sample collection mechanisms. We have two. One is the drilling, but not this one. On the other side. So you can see that it's already have a drill deep under the surface, but on the other side. And this is for drilling. And also we have a robotic arm with scoop on its end to collect samples on the surface. Both, we will discuss this later. So this is a bigger image of the collecting mechanism. So the sample collection is very, very complex. As I mentioned, the environment is very crucial. And the thermal control is a big problem. So we choose the thermal control bus based on fluids. based on the phase change of water. So it's very effective.
Yeah.
And after collecting samples, as I mentioned, will be the liftoff of the ascender,
yeah.
the ascender. So you see that it is very special in multiple features. You see, first, during the former missions of Chang'e-3 and Chang'e-4, you see that because we only need to land on the lunar surface and
Yeah.
no longer move again.
Yeah.
And also, we only need to release the rover. So that will be the end of its operation, except the payloads. But this time, we need to lift off again. So the sensors and also instruments necessary for flying has already finished its task in Chang'e-3 and Chang'e-4 missions. But for this Chang'e-5 mission, you see, they need to work again.
Yeah.
So that is reason we made a cover on the land on the ascender, because you see we have multiple instruments such as the we call the star sensor. The star sensor is a very precise instrument to measure the attitude of the vehicle itself by monitoring the images of the stars and getting the relative attitude. So you see, this is a very precise optical instrument. It can be influenced by the lunar dust. So we made a cover when. Before the landing, the star sensor just cover its lens and avoid the influence of the lunar dust. So after collection of the samples, remove the cover and it can be used again. So this is one of the examples of the very special design of the ascender.
That's very fun.
Yes.
Fun fact.
Yes, and also you see that to reduce the mass, because every gram is very valuable. You see, in the missions before, although we have a similar landing procedure, but this time the CPU or the brain of the vehicle is on the ascender, not on the lander.
Oh,
so,
okay.
Although
so that's a part make it smarter, right?
Exactly.
Yeah.
So you see, although the landing procedure is mainly achieved by the lander, but its brain is on the ascender. And so this is different. And also, you see, this is to reduce the weight, because it need to use the brain again to lift off. So this is also a very
bring the sample back to the returner.
Yes, exactly. And another difference is that you see that the Chang'e-3 and the Chang'e-4 probe has a mass of 3.78 tons. But you know that, as I mentioned, they also need to have orbit insertion from the translunar orbit to the circumlunar orbit. So after it entering the lunar orbit, it already used a large amount of propellants. So it's much lighter than the original ones. But this time, you see that the orbit insertion is achieved by this orbiter. So during the landing, the lander almost have all its propellant tanks full of propellants. So it's much more heavier. So you see, this brings a problem. The landing gears have much serious impact during the landing than the Chang'e-3 and Chang'e-4 missions. So this is also a difference. Another difference
So how do we do that? It's so heavy
so
when
we
it's landing.
must design and perform many tests to prove that the landing gears can afford these impacts.
Okay.
And also there is another difference. You see that because we don't need to lift off again in Chang'e-3 and Chang'e-4 missions, so there is no very strict requirement to the flatness of the landing site. But this time, because you see we want to lift off again, so during the landing procedure, we must choose a place much more precise than the former missions to be flat. And this time, it's really perfect. From the measuring data, we can know that the lander landed to a place with 0 degree on one direction, and on the other direction, only 2 degrees. So it's really almost a flat place for the liftoff. Very, very ideal. So then we have a liftoff from the lunar surface.
Yeah.
And then, as I mentioned, the rendezvous and the docking on the lunar orbit. And the sample transfer is also very difficult. You see that there are similar problems. You see, in vacuum communication, in our professional field, we have two words called cold welding and dry friction. This is caused by the vacuum condition. If two surfaces attach to each other in a vacuum condition with the cold welding and dry friction, it cannot separate again. So we must have very special treatment to the surfaces of the moving parts, either the robotic arm or the docking mechanism. So, and the docking mechanism is quite different from those we used on the Shenzhou spaceship and on the Tiangong laboratory. You see, this time, because you know that the two spacecraft, the combination of the orbiter and the returner during the rendezvous and docking is about, the mass is 2.4 tons. While the ascender, after ascend, the original mass is about 800 kilograms. And because the liftoff, you know that, as mentioned, the orbiting speed is about 1.6 to 1.7 kilometers per second. So after it returned to its orbit, it's almost used all its propellants, and the remaining mass is about 400 kilograms. So you see, this is 2.4 tons, and this is too small comparing with this one. So the docking must be carefully designed. The approaching speed of the final phase is less than 1 centimeter per second. How slow it is, and must be very accurate. And we use a very special mechanism. You see, during this design, we have a consideration. Look, the lander must land on the moon and change its speed about 2,000 meters per second, and the ascender also need to change its speed about from 0 to 1.7 kilometers per second. So the total change of velocity is more than 4 kilometers per second, very huge. So you can see that either both the lander and the ascender, more than half of their mass are propellants. So we must save every gram of mass. So on its docking mechanism, we try to make it more simple. Yeah. So the mechanism on the ascender side will only have 3 sticks, and on the orbiter side, which is on this adapter, the docking mechanism have some claws to grab these sticks, and when it holds to the end, it can be precisely docked, connected, and then we use the transfer mechanism with 3 poles, grab 4 times, and then transfer the sample container from one side to the other.
Yeah, so we can see it's a very complicated process. And we know that the American astronauts, they collect the lunar sample by astronauts, and the former Soviet Union, they collect the lunar sample by the probes, but they're only like 300 grams. But this time, China collects about 2 kilograms. So how do we do that? What preparations have we made to collect and drill as much samples as possible? How do we achieve that?
What we've already discussed, the whole procedure answers this question. Yeah. You see, when you want to land on onto the lunar surface from a lunar orbit, you need to change your speed for 2,000 meters per second. So most of the vehicle are propellants. And when you lift off from the lunar surface, you need another 2,000 meters per second. So if you use the manner like the former Soviet Union, so they choose a very simple way. They don't have a lunar orbit rendezvous. They only have a lander and the ascender, and the returner is on here, here. So it's much more simple. But that means that those mass or the measures we use for the re-entry to the Earth is also landed on the lunar surface. Okay. So it's a waste of resources. And also lift off. They need to lift all these mass to the ascender. So although you see that our Chang'e-5 probe is 8.2 tons, and the lunar probes from the former Soviet Union is about 5.8 tons, we only 40% heavier than theirs. But we can have the samples almost 20 times heavier than their samples. So that is the reason, because we choose a lunar orbit rendezvous, and those necessary for landing and liftoff are not mounted on the orbiter, and those for return to the Earth are not mounted on the lander and ascender. So that is the reason we can be heavier. And you see that all this procedure we described is very, very similar to the manned mission, like the Apollo mission. So you see, the Apollo mission, the Apollo spaceship also have 4 parts. The lunar module of the Apollo program have a descent stage and the ascent stage. I believe that the descent stage is equivalent to our lander, and the ascent stage is like our ascender. And also the Apollo spaceship has a mothership called CSM, or commander and service module. So the service module is like our orbiter, and the command module, which finally return is like our returner.
Yeah.
So you can see almost the same configuration. So our mission profile is as complex as the Apollo program. This is our feature to to use the resources to the maximum extent. And with this measure, as you asked, we can get much more samples than the former Soviet Union. Yeah. But the problems also comes because you know that for manned missions, the astronauts can handle uncertain situations. Well, this time it's an automatic one, a manned one. So it must be highly autonomous and it must be consider many uncertainties.
Yeah, so we have two ways to collect the samples. The first one is drilling, and the second one is collected from the surface. So what are their advantages and what are their functions respectively?
Oh, we can have two aspects. From the engineering aspect, you see that, as we have already discussed, the lunar surface is very, very crucial environment. Mm-hmm. It's very risky, and because this is the first time we've done it, yeah. So the drilling, look, the drilling here and also the scooping are different measures with different technologies. Yeah. So each can be recognized as backup of the other one. If one failed, we still have a chance from the other side. So this can increase the success rate of our sample collection procedure. Mm-hmm. So this is consideration from the engineering aspect. And from the scientific research, both are very useful. You know that, as we have discussed, we want to know the history of the moon. Well, you see that on the lunar surface, the regolith or the soil are influenced by the solar wind and also by the extreme high and extreme low temperatures of the moon. So many information are damaged. So if we can drill deep under the surface, we can get some original examples. It is very interesting. You see that the drill, the stick, the drill here, mm-hmm. It is hollow inside. It is hollow inside, and we have some soft bags inside. And when we drill deep about 2 meters under mm-hmm. the surface, we can seal the soft bag and then drag it up.
That's
and then,
very interesting.
You notice that, you see that beneath the lunar surface, there are different layers of soil. Yeah. And the order or the sequence is also a very useful information because in different era, there are different layers. So we also, during the drilling, we also keep this information because this is also very important for our scientists to know to study the evolution or the history of the moon. And also, you see, as I mentioned, the solar wind have very serious influence to the soils on the surface. And this is also a very good field for our scientists to study because you know that we would discuss about helium-3. Where did the helium-3 come from? It comes from the solar wind. So all the resources of helium-3 are getting from the sun and inside the soils on the surface. So studying the influence of the solar wind, studies the lunar surface environment is also very important for us, for scientific research. And also, this is very useful for the purpose in the future if we want to know that how we can construct a lunar base on the lunar surface. So you can see both the drilling and the scooping have their scientific research meanings. So both are very useful.
Okay, so now we're lucky to have a reporter online. So he's very lucky that he's on site to witness the miracle, the very marvelous moment of the Chang'e-5. So let's do an online video to talk with him. While we're waiting, we talk about the drilling process. I noticed that there is a very interesting... Oh, hi. Hello, Jianhua. Hi, nice to have you. Say hi to our expert. I'm fine. We're doing the live streaming, and it's extremely fun because we talk about the whole process of the Chang'e-5 and also the Long March 5 series. So let's talk about you. We know that... Can we see that? Yeah, so you're on site, you witnessed the whole process. So what was your mood? Tell us, share with us your feelings.
Yeah, it was a very exciting moment to be in it. But the thing is, it was freezing cold. It was minus 30 degrees. So the thing that most people
Yeah.
there was concerning about, were worried about the weather. It was so cold. Also, it was quite windy. And then, so when it comes to the specific landing spot, because of the strong winds, that the routes probably would be waylaid because of the weather. And then also when it came to this small town, and then I felt the vibe of this town. If you look around, and then you would realize many of the names of the restaurants, the schools, and many of them actually were named after Shenzhou, because starting in 2003 when Chang'e-5 landed here, and this is one banner in Mongolia, and then this town became a household name. So I knew about it, but I've never been here before. And when I landed, and I felt the vibe of this small town, and also I was quite curious about this whole process. How do you find the return vehicle? We call it returner. So it was very exciting, and I was very happy about this whole trip.
Yeah, we always call this mission very special. So from your perspective and what you have been witnessing in the on site, what's so special about this mission?
Yeah, I think Professor Yang talked about the special, when it comes to this special mission, and a lot. I'm going to talk about my feeling for covering this whole event, this historic moments in China. So we started around 11 p.m. and then we drove for about 1 hour, probably one and a half hours. And then, so we got a specific or designated area for the media outlet. And we waited there for about 2 hours until it landed around 2 or 1:59 to be specific. And then after that, we drove into basically nowhere. It was totally in the wild. It was so cold too. And then there were so many cars, so many SUVs, around 50 of them. And then we drove all the way to the specific landing spots. But at the very moment, and I was also quite surprised that it took the ground crew only about 40 minutes to find the specific landing spot. And then when we arrived around the area for its landing, we were denied access in the first place. And then after that, they had to make sure that everything was okay for the media people, and then we went in. There were so many people, it was totally packed. So we squeezed, shoveled and pushed all the way through, and then I got very close to the return vehicle, probably only around 5 meters or 6 feet, around that much. And then, so many people were taking pictures there. And then, so because we were doing live, and also we had the vlog filmed by then, so I was quite busy about it. But all in all, it was a very exciting experience.
Yeah, so what preparations and organization work have they done on the ground?
A lot of preparation, actually. Ever since its launch at the end of November, many of the engineers actually flew here to the this small banner that is termed in Mongolia. So it is very much equivalent to a town in inland China. And they came over here, and then they had several rounds of drills, probably three days before the predicted landing date. And then there were 3 teams, on the ground. We were with ground 1 because it was most likely for ground crew 1 to find it, so it was easier for all of the reporters or the media people. And when it comes to the equipment, so I had a tour around the camp. So they have all kinds of equipment and facilities, like the loading truck. The loading truck will pick it up, the return vehicle, and then the return vehicle was flown to Beijing for analysis. And one thing that impressed me the most, and that is the Caterpillar loader, just in case if the return vehicle lands in a pit, and that was the only vehicle that could get access to the returner. And also, it was not only about the ground crew, it was like a coordinated effort. I also visited the aerial crew. There were altogether 6 helicopters back then. So mostly through the satellite navigation and telecommunication networks, the aerial crew would usually find the specific location first, and then they relay the message and the location of the landing spot to the ground crew, and then the ground crew will go there after, and also visited the satellite management and control center. They also had several rounds of drills to make sure that everything was going smoothly on the D-Day. Rachel?
Yep. Thank you so much to share with us your insights at the site with the Chang'e probe launch. Thank you so much.
Thank you so much.
Yeah, looking forward to talk to you in person back in Beijing. Bye. See ya.
Bye.
Okay. Yeah. So Zhenhua shared with us his insights on the site. So let's go back to the drilling process. You mentioned that there are some very completed procedures, and I've noticed that there's a very interesting picture about the stick do the drilling job. So there's a stick, and the bottom is black, and the rest of it are white. So why have we designed like this?
This is the reason is that you see. We don't know the hardness of the soil.
Yeah.
We don't know that we will dig into the soft soil or very hard rock.
Yeah.
So we must make it hard enough. So these parts are made by a very hard material to have a very effective drilling procedure. And also you see that, as I mentioned, every gram is valuable. So to reduce the weight of the whole drilling mechanism, so we use a different, because it no longer need to be very hard. So we use a different material to reduce the weight.
Yeah. So when the ascender got the samples, he must return to the orbit. So that's where I think the big challenge is, because you have to complete the docking. But docking, in the vast universe is like putting a needle in the thread in the spread. So I think it's very complicated. How do we achieve that? How do we put the dockings of the ascender and also the orbiter?
Generally speaking, we have two phases: the long-distance guidance and the near-distance guidance. You see that during the liftoff of the ascender, they cannot see each other with the orbiter. So you see this time, the orbit of each other, or if they want to know the position of each other, mainly based on the information informed by the ground. So you see, as I mentioned, we have the Jiangsu Deep Space Station, we have the Kashi Deep Station, and also we have the VLBI links, and all these are used to measure the orbit of the ascender.
Okay.
And during this process, this time I'm very happy to see that from the report that the our station in Namibia and also our station in Argentina, as I mentioned, also joined this VLBI network. So you see what this means. This means that in the years before, we used our VLBI, very long baseline interferometry from Chang'e-1 to Chang'e-4 missions, but the length of the baseline is about 4,000 kilometers. The longer it is, the accuracy, more accuracy it is. But this time, with the joint of the Namibia station and Argentina station, the baseline prolonged from 4,000 kilometers to about 10,000 kilometers. So it's more accurate this time.
Okay.
And also, we use other special technologies. For instance, we emit signals from the Jiangsu station with a 66-meter antenna, and the other stations, like the stations in Kashi and also our stations in Xiamen and in Qingdao, all these stations receive the signals. And we combine them together and have the process, and we can have a more precise prediction of the orbit. So this is very important for us in the long-range guidance phase to have a very precise orbit of the ascender, although it's mainly flight on its own. So after this, we will have to get possible for them approaching to each other within the distance about 50 kilometers. And when they approach to this, to this distance, the two vehicles, so they will based mainly on the rendezvous and docking microwaves. So this rendezvous and docking microwave we can recognize it as a derivative of the rendezvous and docking microwave radar we used on board the Shenzhou spaceship and our Tiangong laboratory and our future space station.
Okay.
But it's even much smaller. Not only much smaller, but also they have additional function, as I mentioned, a vehicle-to-vehicle data link. Because each vehicle is to exchange its position, velocity, attitude, and other status information to the other one. So also, this radar has this function, and it is very small. All these instruments I mentioned are mounted here. Look, mounted here, because they only be useful during the docking and rendezvous, but not useful in the following procedures. So after the docking, it will be jettisoned.
Okay.
To save the weight. And you see that from this distance, about 50 to 100 kilometers, we mainly based on the microwave radar. After that, we will use the LiDAR or the laser radar. We also have reflectors on the other side to measure the precise distance. And then we use the optical sensors, which can have the measurement of the final approach. And then with this help, we finally can get to each other with a speed, the relative speed, as I mentioned, less than 1 centimeters per second. And the cloud on the orbiter side grab the sticks on the ascender side, and when hold it to the end, there is a V-shaped slot. When the stick come into the V-shaped slot, the two vehicles can be precisely connected with the right position, the right attitude, and also make a preparation for the sample transfer.
Okay, so let's go back to the desk to see our comments from our online users, to see if they have any questions to ask you. So let's check the comments. If you have any questions, you are welcome to leave your comments here. And we have the top experts to answer your questions in person.
Every question is welcome.
Yeah, so there's a question why the lunar probe is named as Chang'e. Can Mr. Yang tell us the story?
Well, you see that this comes from our traditional Chinese mythology, that you know that Chang'e is a moon goddess in China. So we named our lunar probes with the name of the most beautiful lunar goddess, Chang'e, have a very good wish for our future. And also, I think it is a really good name for us.
Okay, so another online user called Sunny asked us that, what about other parts? Where's the lander? Where's the sender? Because we know the returner, they come back to Earth with a lunar sample. But what happens with the sender, with the lander, and also with the orbiter? What happens to
Well, you
them?
see, after collecting the samples and after the liftoff of the ascender, the lander have accomplished its task.
Yeah.
So it will remain permanently on its landing site. Actually speaking, with a latitude of about 43 degrees, and with the attitude, sorry, I don't know, remember exact figure, but it's in the ocean of storms, just to the north of the Mount Stromker. So this region has a very young volcanic activity, so permanent stay there. And very interesting, look, the US has a lunar orbiter called the Lunar Reconnaissance Orbiter, which have very high resolution cameras, just take photos of our lander. So it is very interesting that the US already get the image of our lander on the lunar surface. Very, very interesting picture. I've seen that on internet. And you see that the lander is on the lunar surface. And after docking between the sender and the orbiter, and after transfer of the samples, both the sender, the docking adapter are jettisoned from the orbiter. So you see, as I mentioned, the original mass of the sender is about 800 kilograms, and after ascending, it used most of its propellants, and it's about 400 kilograms during the docking. And after jettisoning from the ascender, it still has some propellants. So we use these propellants to reduce or lower its altitude and to let it crash on the lunar surface. So this is to avoid to make it rubbish or space debris on the lunar orbit. So we're concerned that in the future, we don't want it to influence other missions. So we deorbit this ascender to let it crash activity on the lunar surface. So now, after this procedure, we only have the orbiter and returner combination. So during its return to the Earth, after it's approaching to the Earth within about 5,000 kilometers at this altitude, there will be a separation between the sender and the orbiter and the returner. And at this moment, the orbiter must have two very important steps. The first, to change its attitude to an attitude which is very fit for the returner. When it's touching the atmosphere, it has the right attitude. This is a very important operation. And after this, there will be a separation between the returner and the orbiter. So the returner, so the orbiter will leave the returner, and then it will have an orbit maneuver. This is to avoid during the descent phase, to avoid the collision of the orbiter with the returner. And after this, the orbiter will deorbit to the atmosphere and burn out in the atmosphere. This is its destination. And after that will be the return of the returner. So you can see all the procedure.
Okay, I see. So thank you so much for Mr. Yang to join us tonight. And I'm so lucky to hear all the class and do all the interaction with you guys. So I remember that I was still a little girl and listened to the bedtime story of the Chang'e lunar story. And now I can witness the whole modern Chinese technology, the Chang'e probe, to get the lunar sample and come back, the whole process. So I feel so lucky to living in this era to witness the whole process, to witness the innovation of the Chinese technology. So next episode, you don't want to stay away because we want to talk about all the Chinese developments in space exploration as well as the world's space exploration history. So we'll still talk about some untold stories. Will there be aliens in the space? And also, is Apollo a fake story? We'll talk about all these legendary stories by our top Chinese expert, Mr. Yang. So Mr. Yang will join us tomorrow, and you feel free to ask your question and leave your comments. So stay tuned. This is Miss Wow. Don't forget to subscribe to my channel, Miss Wow, on Facebook, YouTube, Twitter, and Instagram. I love you guys. Bye. See you next time.
Bye-bye.